Good morning and good afternoon, everyone. Welcome to join the webinar Towards a New Paradigm, Virtual Testing and Operation in Aviation, the 6th edition of Connected series, which focuses on Sino-Swiss collaboration projects and research efforts. My name is Li Binggu. I'm the head of academic relations at SwissNext China, Science Consulate of Switzerland in China. We connect the dots between Switzerland and China in education, research, and innovation. Today, we are very delighted to have two experts from Zurich University of Applied Sciences and Beihang University to share the latest developments in their research in virtual design and operation of aircrafts and discuss the key challenges. I would like to kindly remind to our audience that at the bottom of the Zoom interface, you can find the Q&A function. So please feel free to type in your questions during the webinar, and we will answer them in the Q&A session. Now, I would like to introduce our first speaker, Professor Dr. Michel Guillaume, head of the Center of Aviation, the leading research hub for aviation in Switzerland at Zurich University of Applied Sciences. He is also the professor for systems integration and structural integrity at the School of Engineering of Zurich University of Applied Sciences and teaches courses at ETH Zurich, TECO Zurich, and University of St. Gallen. Professor Dr. Guillaume obtained his PhD from ETH Zurich in 1994. His expertise and research interests focus on aerodynamics, aircraft design, structural integrity, damage tolerance, and fatigue analysis. Now, Professor Dr. Guillaume, the floor is yours.
So, good afternoon, everybody. First, I want to thank you to SwissNext in China for this opportunity to having this presentation here, especially to Li Binggu for supporting us and preparing all this webinar. So my presentation will be about virtual design and operation for the optimization of the life cycle. Next slide, please. So first of all, I want to mention important is the physics. And even in the first flight in aviation, powered flight, in 1903, by the Wright brothers, physics was important. They have done a lot of testing. They have done wind tunnel testing to design their aircraft. They have done some structural testing. And important is the physics. So the weight has to be somehow maintained by lift. So we need to have lift capabilities. Then we had to have drag. So have to compensate drag propulsion. And don't forget, and that's very important, I always tell to my students, it's even more if you design an aircraft. You have to take care about stability, control, and handling qualities. Even today, where we have fly-wire software, handling qualities in the term of computing science is important. It's a new dimension than having a pilot on board. We do everything manually, but nevertheless, important is we still have, even if we talk about simulation or virtual design or operation, the human in the loop is quite important. So just talk about autonomous cars, taking out the driver or saying, okay, there's no steering wheel. That's a big step. We are not yet there, but we'll go to more autonomous systems and directions. So please, next slide. So an aircraft is a complex system. I was involved in the design and in many safety discussions on the Airbus A380. That was a tremendous project. That was a really complex system. You see how many systems we have. It's not only airframe structure, it's not only flight control system by fly-wire, it's energy distribution, fuel system, electrical systems, connectivity with data links, engines, and so on, auxiliary power unit. So it's really a complex system, bring all together. And the A380, you can say, is the flying system with 250,000 sensors. So sensor network system. And even that, the A380, most people do not know that, is more or less the father of the more electrical aircraft. All people think it's a Boeing 787. Yes, they get even faster in a Boeing 787, but really bring more electric systems on board. That was the first plane, is the A380. And what's important is systems engineering. You will see next talk by my colleague, Dr. Han. He will show you the V model of system engineering. So the basis today in a system design is the V model. So it's really taking systems into account, system aspect, because at the end, we need to manage the interfaces, not only physical, as in the first flight, 1903, that was more physical interface. Today, we have a lot of information, HTML files and so on, protocols interface. That has to be taken into account. Otherwise, our aircraft will not be certified on time and will not be successfully operated by the airlines. So next slide, please. I just want to tell you how easy it was designing the Douglas DC-3 requirements. First of all, it was not a brand new aircraft. It was a successor of the DC-2 and was a very simple 3-page request for proposal. Today, we have hundreds of pages. In military system, that is gigabytes, terabytes requirements for a military system. So it's very complex, but it was easy. So it just was a marathon phone call with one the stakeholder or the customer, which was Mr. Smith from the airline and Mr. Douglas, as CEO from the Douglas company. The key requirements here: range, cruise speed, passengers, twin engine, and important, don't forget that ratchet and economical. That was important for the operators, for the airlines. They want to have an economical airplane, a ratchet airplane. So that was very important. And that airplane was a first flight in 17 December 1935. And over 10,000 airplanes were built, especially for military application, as called Dakota. I also want to remind that the lift to drag ratio, which is a physical number, it's okay. You can switch to the next slide, it's okay. So the lift to drag ratio was already 14. Today, the max lift to drag ratio, which is an aerodynamic parameter, lies between 18 and 20 of our modern commercial airplanes. So requirements evolved dramatically since the 70s, even more. Today, we have to take care about security. For example, cyber security. They need more demands. We have more demands from the customer, from the stakeholders. And as you see on the A380, it's a network sensor platform. So we have to share data with the original equipment manufacturers, let's say Boeing, Airbus, or Comac in your sense, or with the airlines, or with the air traffic management system. So it's a lot of data chains, a lot of requirements, which makes our design complex, and we can only maintain it with computer and with doing really virtual work simulations. Next slide, please. So when I talk about system considerations, important is the system performance and the system availability. If you're an airline, you want to operate the system. You want to be in the air. You want to transport passengers or cargo. So you want to really have high availability of all the systems, of spare parts, and so that's very important. So we talk about technical effectiveness. So your system needs to be technical effectiveness. That's important in the content of systems engineering, of system design, and also of the operation during the whole life cycle. Nevertheless, operations, even if we design aircraft, we have to think about the operations, about the maintenance and the logistics of spare parts. So process efficiency is quite important. At the end, we need to talk about a so-called total system effectiveness, which means affordable operation effectiveness. So it's quite important. And at the end, when you design something, you always need to have the end in mind. That's quite important. And you see other considerations, which are safety systems, human factors. I want to highlight human factors. Even when we talk about virtual design, there's still humans doing design, doing algorithms, working on artificial intelligence. That's important. Still humans. So we should not eliminate the humans. We should even think more, what are the rules on the humans in the future? Who will make the key decisions? Can autonomous systems make key decisions on where are the limits? That are discussions we have to address now when we talk about virtual design and virtual operation. Next slide, please. So what is product life cycle? It starts first of all with the definition, with the concept, definition, design, build, test, and then you certify the project according to standards, and then you operate. You can say the time frame from concept to test certification may be 6, 8, or 10 years, today in an aircraft program, the operation is about 20, 25 years. So it has quite last long time. And the challenge in there is, will there be all suppliers still alive? What is the evolution of technology in that 25 years? So if you have a software code of your flight computer, you have to maintain for 25 years, that's a real challenge. Or how change domestic markets? Just A380. The A380, 20 years ago, we talked about the great market. Today, the A380 is out of business. We'll retire the A380s now because it's no more demand in market. We have commercial pressures, customer economies. The customer want to have an efficient plane. So that are things which may change over time when you operate the plane over 25 years, which has to accommodate, which is quite a challenge today. There are forecasts for so long. Today we discuss in business about 3 months or 1 year. We have no long perspective. So that's a real challenge in the aviation industry because you have very long terms for our product in service life. Next slide, please. That chart, more or less the basic idea of having conceptual design using optimization or multiple optimization, physical optimizations, started already 20 years ago in academia. I was part of that. I was a part of the CISM consortium in early days. So there we tried to bring with optimization all the tools together to design an aircraft, to do a preliminary design. So we need to have aircraft builder, we need to have 3D mesh generators, structures, that's all structures, aeroelastic modeling, we need to take engine integrations, and we do flight physics, flight control systems, so stability control, as I mentioned, so all together to design the whole aircraft system. Today, that's more or less state of the art in every aerospace company. So they use that to their operation now. They use that to design new planes, but originally that started 20 years ago. And one of the challenges is in that regard is the human. We saw at the beginning, we can optimize everything by computer, just running virtual for system. What we figured out, even taking now into account artificial intelligence on top of it, sometimes you get solutions which are not practicable, which are physically nonsense. So there we had to integrate in certain steps the humans, the experts, which make decisions. That was a key decision of 20 years of multiple optimization design. So the key measure is where is the human, where it takes the decisions. That is quite important. We don't need to forget that when we talk about the virtual design and operations. Next slide, please. I just want to highlight a little bit the virtual airframe design. So we have about 5 levels. First, you do have an aircraft layout. Then you go more details on the example of the fuselage barrel. So then you think how it looks like, what are components, what materials I use, composite, metals or hybrid. Then you have to go into more micro level designs, details. And in level 5, you have to also address manufacturing process, strength, buckling, so to make sure that all the structure holds together, have a structural integrity, durability to life. We designed to a certain lifetime, and also address potential repairs. That is a challenge with the new composite planes. We don't have for every event and instance so far repairs. You need to know that. So that's a challenge. We need to think ahead of that. So important things is geometrical parameters, loads and structure determine loads by simulation, computers, or by internal testing, safety, ecology, long-term strength, that's important. We're taking about 25 years of operation, but also manufacturing, maintenance, repair in the beginning. One thing you don't need to forget the tolerances. If you build an aircraft or every product, you need to address tolerances. Some parts need to be replaceable, interchangeable. That's quite important. That's hands-on experience. So the question is how we can bring that experience into virtual design. I think that is a real challenge. Next slide, please. As you heard, I'm an expert in aircraft structural integrity. So I want to show a little bit where we go in virtual testing for certification. On the left-hand side, you see the classical building block approach up to material qualification, coupon testing. Then you go more higher elements of structural elements, sub-assemblies, subsystems of barrels, and then a full aircraft. So we do full aircraft testing, static and fatigue. Today, we test about 3 times service life to make sure that we have any widespread fatigue damage, so that you have multiple elements in the fuselage affected by cracks. So we ensure that But the goal today is going to more virtual testing. So can we do static testing for certification just by simulations? That is a big discussion now. In fatigue testing, can we reduce the test time and the test, which costs a lot of money, by doing more virtual testing for fatigue certification and only doing limited testing, still of an airframe, but to address and reduce the development time. So you see that on the left-hand side, we're going more and more virtual testing simulations. But I think we are good today. All our tools and methods are calibrated for wing tube designs aircraft. So for that, we are good. If we're going to blend wing body design, I think we should do more going back to basics, to the physics, adjust our tools and methodologies. So we need to do more testing in wind tunnel or structure test to get familiar with the new concepts. And then we can calibrate somehow a simulation basis and then go into more simulation and world testing. So if we really come up with new designs, which don't have experience, then we need to go maybe a step back and do more tests and validate all the methods and technologies. Next slide, please. So today when we design an aircraft or any system, we talk about digital twin. That word I heard first time 20 years ago from the US Air Force. So it's not brand new. It's a hype today a little bit, but I think we have digital databases. I was involved in wind tunnel testing of the Falcon 5, 6, or 7 series and 8. So they really pushed ahead with so-called digital design. So there are full digital mock-ups today, as you see here on the left-hand side. So you can really try already in the pre-design phase, coming up with some how we assemble the aircraft, how we do maintenance. So we can really address that. We can work with artificial intelligence, virtual reality to really make good product also for the operation. So already design, we can take more into account for the operation purpose because we have so-called digital technologies, which are quite important and those heavily used on the Falcon series on every aircraft today. So digital design is important and the digital database is the basis for then also in the operation to use it as a so-called basic scientific network system for the future. Next slide. So if you're an operator, an airline with a long-range aircraft, let's say a Boeing, Airbus, or your new COMAC product, then your goal is to stay as long as possible in the air. So you want to really get cash from your passenger or cargo. So operating goals for long range is about 18 hours in the air. So for that, you need high reliability, maintainability. And as I mentioned, just an example, the A380, it's a central network system today with a lot of sensors. We can use the data to maintain the aircraft in the air, on the ground. And can you slow me the next slide, please? So we can use a lot of data to optimize the operation, to optimize the maintenance, and that even will help us with maintainability, reliability, and safety at the end. So that's quite important. But we need to have data links. The disadvantage of data links is a limitation in frequency. We need frequency bandwidths. That's a challenge. But on the next slide, please. The ACAR systems. The ACAR system is quite old. Was developed in the 70s for so-called VHF communication. So the ACARS is called Aircraft Communications Addressing and Reporting Systems. And I think that's just an example. We need such systems for sending sensor data to the aircraft, but from the ground to the aircraft. So today, for example, the airline operators, the technical department surveys the monitoring the engines. So you know in advance if there's a problem on an engine, for example. That can be even go further for further systems. I think a pre-drive could be what we do in monitoring on the engines. That could be first run for other systems. So that you're well prepared when the airplane comes on the ground. We know we need to replace the system or even having a bigger maintenance and replace the aircraft. So with that, with data links and sensors, we can really improve that. But my proposal, and that's a future proposal, that's not yet done, is maybe we maintain a virtual operation on the ground, maybe in a simple rig with a lot of data. We feed operational data from the sensor of all the airlines, and we simulate where's the next problem in the system, where we have an interface problem, to be well prepared to maintain the aircraft before we get failures or we get an accident or a tragedy, a disaster of an aircraft, that you can really optimize from the point of availability, economically, the operation for the whole lifetime. So next slide, please. So that means full simulation of operation. So we need to take care of the aerodynamics, the gas loads from the weather storms. We need to take care of ground events or air events. And you see here on the left-hand side, bottom line, we have a lot of sensors which we need to communicate back. We need decisions. Do we report directly on a data link, or do we download data on the ground? So that's quite important, how we manage that. So that we need to have standards, we need to have protocols, and maybe on the right-hand side on bottom, maybe we still need to have so-called like an Iron Bird system, which you need for certification, that will have more or less an Iron Bird running further off certification to gain more experience with the real system in operation. Because when you do flight testing for certification, you do about 2,000 to 3,000 flights. And as soon the airline starts operations, you accumulate much more hours. And then you are beyond the experience how you certified the airplane. You make sure everything is safe and secure, but then you can further issues. And if you have maybe a virtual operation, we can tackle them first before them appear in the real life on the operation. Next slide, please. So I came to my summary. There are challenges and threats. I think we will more work virtual, even in teams, virtual teams. That COVID-19 even progresses that. That's quite important. So we learn here quite fast. Nevertheless, in aviation, safety is first on every flight. So we have to make sure we can maintain safety. I mentioned the human in the loop in virtual design. A lot is important. We need to have a good mix of design, past experience, how we feed past experience in digital database from sensors, also operation data. I think we need to discuss heavily on data standards and integrity of data availability. Some operators don't want to share their data with the manufacturer, with let's say Airbus, Boeing. They want to keep them themselves to have more advantage in the so-called knowledge. And important, also cybersecurity will be a big issue. I mentioned already data link capacity, the bandwidth frequencies. That's quite important, even for coming up unmanned aviation. There we had some challenges, physical challenges. I think the cost of maintaining data for 25 years is a big issue. I see the military aviation. I was involved in the F-18 for the Swiss Air Force during the redesign. And we see now operation the plane for 25 years, taking data on old computers, how we mitigate fit that. Just keep in mind what computers you had 25 years ago, what you have today, what you have in 10 years, how we can maintain this data, how we can maintain the knowledge. A 747 Boeing, you still have a floppy disk in the cockpit where you update your software. So we need to take that into account. So really the challenge is designing life of airplane and operation over 20 years, long period of technology route. That is a real challenge. And at the end, when you talk about digitalization, virtual design testing, I just had about 8 years ago a talk with Aviation. So they say, okay, yes, we do more aerodynamic simulation with computer fluid dynamics. The energy, what you need to run the computers to store data is more or less today becoming in the order of the energy of a wind tunnel. But the technology also in the wind tunnel evolved, so we can test much faster. So the energy consumption, what we need for design with efficient testing on a wind tunnel, for example, and doing compilation fluid dynamics is more or less the same amount of energy. We're talking low speed dynamics about 3 to 5 megawatts, just keep in mind. So there we have increasing demand of energy. And we have to maintain sustainable energy, though that's renewable energy. That is quite a big challenge. And we should think about more, can we afford digitalization to every bit and bytes at the end? And last slide, please. So I want to thank you very much for your attention. I hope it was interesting for you. And I'm happy to be on time. Thank you very much. And I'm happy at the end to answer Q&A. Thank you very much. Thanks.
Okay, thank you, Professor Dr. Guillaume, for the interesting talk. Now I'm delighted to introduce our second speaker, Dr. Xu Han. He is currently a postdoctoral researcher at Beihang University. He received his bachelor degree in mechanical engineering from Yanshan University and master and PhD degree in mechatronics from Beihang University. His research interests include hydraulic transmission and control, electrohydrostatic actuator, mechatronic system, modeling and simulation, design and optimization. Dr. Han, the floor is yours.
Okay, can you hear me? Okay. Thanks, Libby. I'm Hello everyone. I'm Xu Han from Beihang University. I would like to present a topic on intelligent design and virtual testing for actuation equipment. Next slide, please. So my talk has three parts. First, the state of the art of this technology, and second, some related work from our group, and at last, a short perspective for this technology. Next slide, please. Next slide, please. Okay, one page back. Thanks. Okay, first I want to say actuators are elementary parts of machinery and vehicles. Nearly all the movable parts are moved by actuators, except for a small amount which are moved directly by human labor. We can have a look at the actuator evolution. So in 1955, the aircraft still use actuators which only consist of mechanical components. Here we can see this is a cylinder which has a rod connect to the load and moving the load. And here a valve which is mechanically controlled. When come to 1969, the actuators on aircraft start to use electronics. We can see both analogically and digitally controlled actuators on aircraft. And when come to 1987, the Airbus A320 use fully digital controlled actuators. And to the current century, the actuators start to beat independent module. With independent module design, the actuator can be more compact and also easy for using. Besides advancing the performance of actuator itself, the developing method is also being improved. Next slide, please. So here we can see the popular V model for the development process of actuators. At the left hand is the design phase. After receiving the requirements, the design starts from conceptual, then preliminary, and then detailed. The right hand is the integration phase for developing actuators. It starts from component level, then system, then testing, and then the development is finished. Now researchers start to use models and computer technology to improve this this model. Next, please. Next. Yeah, thanks. So we can see researchers start to use models and other intelligent algorithms to make the design more optimized, and the models can help to mitigate the risks and also omit some physical tests. Also, researchers combine some intelligent algorithms to make the design more automatic and intelligent. So let's see how to implement this model-based design and testing. Next slide, please. First first step is conceptual design. We can see here. First, the actuator should be decomposed into sub-function. This is based on mostly based on the component configuration. For example, the F1 represent the power generation, F2 represent the power transmission, F3 represents the final acting part to move the load. After decomposing the functions, now the computer can start to continue the designing instead of human. So the computer can automatically search the solutions with all the possible combination of sub-functions, can also be called components. And the computer can also have automatic selection for the possible architectures of the actuators. So this is based on models and interval arithmetic. Because in this stage, there is not so detailed information, so we can't define an exact parameter of the actuator. We can only design an interval. And the models is also static models, not dynamic models. But with this simple method, we can finally achieve a small amount of architectures which has better performance than other solutions and be transferred to the next design stage, preliminary design. Next slide, please. So for the preliminary design, we should first build a causal models for is a model library, and with the models are all component models which can consist the actuators. After we have this model library, we can build the entire actuator model, which called causal modeling. So the method is just similar with the physical assembly of the actuator. We take blocks from the library and assemble the actuator model and then start the simulation. The simulation is controlled by an optimizer, which can automatically search for better performance solution and with limited time. This can't be achieved by a human designer because human can't have hundreds or thousands of iteration of the design. Next slide, please. So here we have some fundamental techniques for implement the preliminary design. First is a multidiscipline modeling method. Although the actuator is not a complex system as aircraft, but it still involves many different disciplines like hydraulic, electric, mechanic, control, and thermal. And also many different requirements should be fulfilled during the design work. So we must build a monolithic model which can involve all the disciplines. Then the actuator can be designed at the system level, and all the attributes should also be involved in the model. So we usually use lumped parameter model, which is efficient and require less parameters, because in the preliminary design, the parameters still hard to achieve. And we prefer Modelica modeling language, which can perform both forward and backward simulation, which can increase the flexibility for the simulation analysis. And the models are usually physical-based object-oriented model. This helps the models can be reused in the other design tasks. We don't need to build a model again and again for different design tasks. Next slide, please. Second, we should consider parameter generation because, as mentioned before, the preliminary don't have so many information for the components and the system. So we need to generate the parameter automatically to perform the simulation. There are two methods. First, we can call it scaling law-based geometry similarity. So we will assume a series of components have the fixed ratio between different geometry dimensions. With this assumption, after we define the major dimension, all the other dimensions and parameters like mass, the moment of inertia can be determined. But this assumption is a little bit rough because that's not always true for components. The geometry have similarity between different models. So there is the second method, scaling law-based dimensional analysis. So the parameter is estimated based on physical reasoning model. So all the parameters which has relation with the estimated parameter are involved in the function. If we want to build this function, we first need to have some samples for this kind of component, and then make a regression to achieve a mathematical approximation for the parameter estimation. At the right side, we can see right bottom, we can see a figure for this example. After we define the dynamic load of a component, we can also achieve other parameters like the mass, the inertia, and this method has relatively high accuracy. Next slide, please. After we finish the modeling, we can start the simulation, which is used for optimization design. First, we should use a multi-objective optimization algorithm because for designing actuators, there are different requirements from the users. All the requirements should be considered at the same time. And also, the optimization should be robust. That's because there are uncertainties for the preliminary design. As mentioned before, the parameters are based on estimation, so the real parameters will different from the parameters are used in the preliminary design. With this in mind, we during the optimization, we shouldn't always choose the minimum value as the result. For example, we can see from left top this curve, the 0.1 is the minimum value. But if there is errors, the actuator performance can vary at the same time, sometimes even unacceptable. So instead, we need to choose another interval, interval 2. Although the central point is not a minimum value, but the entire interval is more robust to the parameter uncertainties. Next slide, please. We also need to develop a surrogate modeling method because during optimization, hundreds or even thousands simulations are need to be performed. If we use a physical-based model, it will be very calculation consuming. So we use these surrogate models to have better calculation efficiency, like polynomial response surface, Kriging models, artificial neural networks. These are all very light mathematical functions with very low calculation cost, but still with a relative high accuracy to predict the performance of the actuator. So this is a necessary technique for optimization design during preliminary design stage. Next slide, please. And then we come to the detailed design. For detailed design, it's much more complex. There's no or all detailed design solution yet. Usually the detailed design still be implemented in individual discipline. For example, we can see the figure here. This is an example for designing the electromagnetic and structural characteristics of electric motor. So the electromagnetic analysis and the structural analysis are done separately in individual simulation environment. And the coupling analysis and the optimization can be achieved by specific algorithms. And at last, after all the characteristics are analyzed, the final solution is formulated. Next slide, please. Then we can go to the virtual testing. For virtual testing, it requires simulation models with higher fidelity because virtual testing is helping designers to gain enough confidence to manufacture their design solution. With these requirements, the co-simulation method is preferred. With co-simulation, different characteristics can be considered in the most sophisticated modeling method. So co-simulation can help the designer to gain the enough confidence to decide to manufacture their design. Here we can see a thermal virtual testing of the electromagnetic actuator. The power performance and also control thermal losses are included in 1D simulink model, and the temperature model is implemented in 3D FEM model. Next slide, please. Next, I want to introduce some work from our group. First, this is a preliminary design method developed by us. We involve the control and thermal attributes. So for the current method, previous method, there are not so many which can consider control and the thermal attribute because this will make the optimization work complex. But we developed this method. First, the models incorporate the thermal module and the control module. And the coupling structure is like a left bottom figure. We involve nearly all the disciplines in this model. And at the right side is the optimization method. To reduce the calculation cost, we use this two-stage optimization. So in the inner loop, no thermal performance is considered. For the outer loop, the thermal performance is considered separately. With this method, we can reduce a lot of calculation cost. Next slide, please. And then we can achieve some results. For example, the dynamic performance of the actuator, which is tested with the sign command here in the top figure. And the bottom is a simulation under a complete duty cycle with 600 seconds. We can see the dynamic evolving process of the temperature for different parts. Next slide, please. And we also developed virtual thermal testing for electrohydraulic actuators. We combine the 1D Lampert parameter model and the 3D CFD model. With this method, we can have relative high accuracy of the temperature prediction, but also a relatively low calculation cost because not all the calculation is done in the costly CFD method. Most calculation is done in the Lampert parameter model, which can achieve high accuracy and low calculation cost at the same time. Next slide, please. And I want to have a short perspectives of the future design method. When we talk about intelligence, we can't neglect the machine learning, very popular at the moment. So how machine learning can help? We want to introduce it to preliminary design first. The first step, we can use it to estimate the model parameters. This is very simple. I think this can be done in a very efficient process. And next, we want to use it for simulation the actuator performance. It means we feed the design variables to the models based on machine learning, and then the models based on machine learning can predict the actuator performance. We wish this can be more efficient and accurate than the current physical-based simulation. And the most exciting goal is to use the machine learning-based model design an actuator directly, which means we just feed the requirements of the actuator to the models based on the machine learning, and then it can output a design solution for the actuator. Of course, this is very challenging because design an actuator is not playing a board game, like playing the chess or classify the images. But at least we can use this method to design some components at first. So it is still deserve to try. Next slide, please. At last, I want to say when actuator experts working industriously within the actuator community, we should also keep an eye on other communities. For example, for the time being, the popular in artificial intelligence, big data, Internet of Things, this kind of technology which is changing our daily life can also help us to make better actuator development. That's all my presentation. Thank you.
Okay, thank you, Dr. Han, for the informative presentation. Now let's come to the Q&A session. So we just have one question from the audience. So we also maybe everyone noticed that there is a Chinese colleague sitting next to Professor Guillaume. So maybe everyone is very curious to know if there are any existing collaboration projects between University of Zurich University of Applied Sciences and Beihang University or Chinese University in general, or what would be the next development regarding the Sino-Swiss collaboration? If Professor Dr. Guillaume, you would like to share some information?
Yes, thank you very much for this question. Indeed, we have a collaboration agreement with Beihang University. I want to introduce my colleague here, which is Xining Liu. He's from China. He studied in Germany in Aachen. So he's a master in aerospace. He's currently working on a PhD, and that PhD is in collaboration with Beihang University. And I think Xining may say a few words on what he's working directly. So Xining can give you some information.
Thank you. Thank you.
Yes, change place.
Yeah. Thank you very much. First of all, I would like to give a short introduction. My name is Xingyin Liu. I'm actually working as a research associate in Zurich University for Applied Sciences in Center of Aviation in team aerodynamics. Actually, I'm also doing some multi-physics simulation, which is also the topic today, I think. And yes, we last year we have a agreement with Beihang University. So we are doing some academic exchanges. For example, Professor Guillaume will probably give the guest lectures in Beihang University for 1 or 2 weeks. And we are also looking forward to having some master students or PhD students from Beihang University in the near future. In the meantime, as a Zeta staff, I'm doing also a doctoral program. It's a doctor engineering in Beihang University. So it's kind of a cooperation between the two universities. So we are looking forward to have more cooperation, some specific project in the future. Thank you.
Thank you. Thank you for your kind introduction about the collaboration background between the two universities. Now come back to the presentations of our two speakers. So we have some questions. So first one would be for Professor Dr. Guillaume. You mentioned on your last slide that about the safety first rule in aviation. So what are some of the main safety related challenges in the virtual design and operation of aircrafts?
I think that the most challenging is where we still have the human in the loop. Virtually, or if you talk about autonomous systems, it looks like the human is no more in touch and no more in control. I think that is still a big gap or a big challenge, because when you work with artificial intelligence, I think we do that in several projects for doing risk assessment on airspace, risk collision modeling, for example, in our center. We use that for maybe using new aerodynamic profiles. At the end, you need to make some checks if that is physically viable, that makes sense or not, and the question where a hoop is still in the loop of making decisions. So I think that is something still will take more time. If you ask me honestly, even when we'll fly a first airplane without any pilot on board or single pilot, I think single pilot operator will come, but even there, he's only a controller, monitoring the system, what his role is, when he can interact or influence this. So I think that's a challenge in safety. And what happens if you only have one pilot on board and he fails, you have a disease or get a heart attack, how we can control it. I think that are changing factors. And at the end, with the complexity, what increases dramatically and will even increase further, with all network, we connect everything together by data sharing, by information. I think there the interfaces will get more complex. How we can understand these interfaces? Surely all the new simulation tools, artificial intelligence, deep learning will help us, but nevertheless, sometimes, and that is changed, we cannot understand fully their algorithms, their solutions. We don't have them under control. So when you have the classical method, model-based physics simulations, it's still deterministics. So we know we have to under control. With deep learning, with neural networks, we may get up some interesting solutions, which sometimes maybe really open our new eyes, which is great. But sometimes they provide a solution which is nonsense. And if you apply that solution, it may lead to a disaster. I think that's a challenge. I don't have the solution, but we need to work on that. We need to spend more research into that. But it's excellent what Elon Musk is doing in the autonomous car industry. But I think even there, the question is, what sensors we use? On the visual sensors? Tesla only uses visual sensors. The German car industry say, oh, we need more sensors, different sensors, ultrasonic cameras, ultrasonic, we need LiDARs and visual. So there is the question, and then, but the complexity is even higher in German car industry because they have 3 sensors. They have to make sensor fusion. So even that, so that is, and where is the human in the loop, controls some outputs and make decisions. I think that's a challenge. And there, safety first aviation, yes, that's our rule. Our mobility is driven by the safety culture. So it's a culture of aviation. We have a culture history, and just in healthcare, we don't have that culture history yet. So I think that is a challenge. How we can keep this culture of safety thinking, of learning from one incident fail to the other. Surely the modern system will help us. We can monitor pilots in the cockpit with cameras, then use that data, analyze data, and then improve their performance or develop some more autonomous system or automatic more systems. But I think it's a challenge. And we have to take care that taking just out human out of a system, it's not easy. It's not straightforward, I think.
Mm-hmm. Thank you. Thank you. You mentioned one very important message is how to figure out the human-machine collaboration. Then I have a question for Dr. Han. You showed us a very interesting example of the application of machine learning in the very beginning stage of the virtual design of actuators. So maybe can you maybe predict or imagine like in the near future, the actuation equipment with the help of machine learning and virtual testing, like how can they bring benefits to us in our life?
Okay. First, in the near future, maybe in 20 years, I think most of the actuators, maybe 70 of the market value can be developed by computer, totally by computer, because most of actuators will have similar features and not so difficult to design. So with this kind of tasks, the computer can design it instead of human. But there are still some other actuators which require cutting edge technique and consider very complex requirements that still need to be done by human. And the benefits is with the intelligent design based on machine learning and virtual testing, the cost and the development time can be reduced, but the performance can be improved. So consider our daily life, for example, for the current cars, the domestic cars, only for the luxury cars, the doors are automatic. And for common cars, with the doors is open and closed by human. But with the intelligent design and water testing, after the cost is reduced, maybe all the cars can employ the actuators for automatic open and close door, and also similar for the aircraft. Not only the business class seats, the seatbelt is controlled, is automatically controlled with an actuator. But after the cost is reduced, maybe all the seats in economic class can also use actuators to automatically control the seat back. So this is the benefits for our daily life.
Thank you very much. Okay, I have one last question for both speakers. What are some possible development and breakthroughs that you foresee in your research field? So in virtual design and operation for aircraft and for actuators in the next 20 years? Professor Dr. Guillaume, please.
I think the virtual design will be state of the art, will shorten design life cycles. What you need to think is if you want to shorten our service life cycles, because we have 25 years, maybe it will be even cheaper to only design an aircraft for 10, 15 years, because the evolution of technology is so huge, because the operation for keeping a system of 25 years long, because I just mentioned the 747, you still have a floppy disk to update the software on the 747. Okay, the 747 is now retired, but it was designed 50 years ago. So basically you need to maintain for so long time. So the question is also, do we with the virtual design, testing capabilities, shorten the life cycles of our aerospace products? That could be a key thing, that if we think, okay, we only design for 12, 15 years or not for 25 years, because then we have more benefits in the operation. And then after, even for sustainability, but just keep in mind, within 10, 15 years, we reduce the evolution or the emissions quite dramatically. So we have new engines today. Every product is coming with new engines, 10, 15 years. So maybe we should think about virtual design, testing, shorten the life cycle of our aerospace products. That may be a key thinking. Nobody mentioned that today. I see any article, but I think we need to think that very hard if that may be a further progress for our future daily life.
Mm-hmm. Thank you. Dr. Han?
For me, because actuators are not so complex as an aircraft, so I think the artificial intelligence and the other computer technology can help the development of actuator more effectively. I'm expecting to incorporate more artificial intelligence, like and also big data, Internet of Things. This can add new features to actuators and also improve performance, reduce cost, because as the first slide in my slides, you can see the actuator is developing slowly in recent decades. So maybe it cost 20 years to have a major difference according to the previous design. But now is a good time. The computer technology is developing very fast, so we can take advantage of this and to have make more difference for the current actuators.
Thank you very much. Well, due to time constraints, we will have to end the Q&A session. So thank you, a great appreciation to Professor Dr. Guillaume and Dr. Han for your available time and your deep insights. And if you have more questions, please send them to the email address on this slide. We will forward them to our speakers. You are also more than welcome to scan the QR code and follow us on our social media channel. Thank you very much for your participation, and we look forward to meeting you in our future events. Thank you once again. Have a nice evening and have a nice day.
Thank you very much. Bye-bye. Good luck.
Bye-bye.
Take
Thank you.
care. Bye-bye.
Thank you.
Thanks. Bye-bye.